When we look at our galaxies and the light from them, the stars, this is sea froth on an ocean of dark matter that's what's actually driving where everything collects in the universe. If dark matter doesn't interact with us, it kind of also doesn't interact with itself, or does it?
Oh, yes, it does. It annihilates. So when two dark matter particles hit each other, they turn into something else. These dark stars start out when they first form being about as massive as the sun. They keep accreting and growing until they can get 1,000,000 times as massive as the sun and 1,000,000,000 times as bright.
This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. As always, I got Chuck Nice with me. Chucky, baby.
Hey, what's happening,
How you doing,
Neil?
man?
That's right. Your personal, no, I'm not your personal comedian.
No.
I'm just going to be honest. Yeah, I don't even want to tell the jokes to a paying public, let alone be available for somebody personally.
Yeah, if the going gets a little dry or boring, say,
Right.
let me, comedian.
Right, exactly.
I need a joke about right here.
Right, yes. Liven it up.
Today, we're calling this episode Going Dark.
Ooh.
Going Dark.
All right.
You got to get low. Going Dark.
Going dark.
Dark. Yeah. This is everything dark in the universe.
Okay.
Yeah, that's a heavily used word lately.
It is.
In the cosmos. Now, while I have a little bit of expertise, I don't have the expertise necessary to devote a whole show to it.
Okay.
So we combed the cosmos and we found...
In the next galaxy over, we found
Katherine Freese. Katie, welcome to StarTalk.
Thank you, Neil.
Yeah.
Happy to be here.
We go back. We came up, basically, we're the same generation coming up through the ranks.
Yep.
And we saw each other at the same conferences and this sort of thing. And
We did.
so it's a just delight to see that. And you've always been interested in these weird stuff in the universe and no one understood what it is or what's going on.
Yeah.
And you're still interested in that.
Yeah, it's a good source of job security.
Astroparticle, the little particles that explain the cosmos on the larger scale.
Yeah.
Ooh.
Very cool stuff.
Yeah, because that's foundational to the
Right.
to whatever understanding would be laced on top of that. So we want to know like, dark matter, dark energy, dark
Right.
stars,
Dark.
dark, just
Right.
everything dark. And you've made a career of this.
I guess I have, yeah.
So let me get some of your resume here. Director of the Weinberg Institute for Theoretical Physics at UT Austin.
Wow.
Weinberg, that would be Steven Weinberg, I guess.
Yes.
Okay, he ended his career at UT Austin. While I was there, he was there. And
And I notice you have his book right there, right
Yeah.
behind Chuck.
Wow.
yeah, it's right here.
That is
Yeah.
the book I learned cosmology from.
Oh, yeah.
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 I was an experimentalist at
Mhm.
Fermilab.
Yeah, gravitation and cosmology.
Yeah.
Principles and applications of the general theory of relativity.
Yeah.
Nice.
So Steven Weinberg, one of the creators of the standard model of particle physics,
Mm-hmm.
one of the great minds of our time,
Mm-hmm.
and his office was 3 doors down from me. And sadly, he died a couple of years ago.
Yeah, he died a few
Wow.
years ago. But then the institute got named in his honor, or was
Yes.
it named while he was there?
No, it was in his honor.
Okay.
Oh, okay.
And we, as of last month, we actually have a webpage.
Okay. Okay. Coming along slowly, but it's there. You're also director of the Texas Center for Cosmology and Astroparticle Physics.
Mhm.
Right.
Man, professor of physics at Stockholm University.
Mhm.
There's a joint position there.
I got this grant 10 years ago
Uh-huh.
from the Swedish government, $15 million over 10 years to do theoretical cosmology.
Nice.
And the way it works is you spend half the year in your home institution
Okay.
and the other half at Stockholm University.
Love it.
So I've had a blast.
Okay. All right. Very cool. Director Emerita. Emerita.
Mhm.
That's the female singular.
Emeritus.
Emeritus, yes, female singular Latin, of Nordita, the Nordic Institute of Theoretical Physics.
Yeah.
Okay.
Mhm.
And
Is there any place you haven't worked? Maybe this would be quicker.
Quicker.
We'll just name the places you have not.
Do you want to hear all the grad schools I went to before I figured out what I want to do? It's a long list.
Really?
Yeah. Yeah. So
You know,
I have alumni status everywhere.
yeah, but that also means you know faculty in different places, and so
I do.
you are very much a fundamental part of the community when everyone knows you and you go to conferences and the like. 10 years ago, you wrote a book, The Cosmic Cocktail, 3 parts dark matter.
Neil, you wrote a blurb for it.
I now that I'm looking at it, I say, I thought I remembered I blurred that.
Wow, is that how many blurbs you've written in your life?
I'm a blurbing dude.
This looks familiar to me.
So, Katie, can you just catch us up on some of what is dark in the universe? So let's just start with the OG dark thing, dark matter.
Dark matter.
Okay.
What's OG?
Original gangster.
Oh, sorry.
You got to get out more, okay? Okay, so dark matter, it's 85% of the gravity we measure in the universe.
Yeah.
Wow.
Yeah.
But we don't know what it is.
Yeah.
So, Katie, if you also still do not know what it is, what do you think it might be?
The best bet is that it's some new kind of fundamental particle. So not neutrons and protons.
Says the particle physicist.
Of course.
Of course she would say that.
Right.
She's a particle physicist.
Oh, well, you know, to a hammer, everything's a nail.
Okay. Okay.
No, I'm joking.
Okay.
That only makes sense, what you said.
All right. So it could be some kind of exotic particle.
Yep. Look, that's
exciting,
that is our best bet.
That's really exciting, though. I mean, but I'm getting way too far ahead.
Aren't you backing into that explanation? You're saying we can't measure it any other way. It must be a particle that doesn't interact with us. But it's real and it's out there, even though we can't see it, can't measure it, but it has gravity. Are we just backing? Is there any other theoretical reason to say that about it?
Well, yes. So the candidates that I consider the best motivated, most of us do, are the ones that killed two birds with one stone.
Good.
So they were invented in particle theories for reasons other than dark matter to solve problems in particle physics.
Oh, so that would give you a little more confidence. If you would have it for one reason and it also solves another,
Yep.
that's good.
Yeah.
Yes.
I didn't know that.
Yeah, good motivation.
Yes.
Yeah.
Okay. That happened with Einstein.
Right.
Einstein comes up with the general theory of relativity, and there's something called the precession of Mercury's orbit.
Right.
Mercury's orbit around the sun did not exactly follow Newton's laws.
Okay.
And we astronomers, we said, there must be some planet that we can't see that's too close to the sun, lost in the glare, and that's tugging on it. That must be it. Yeah. And we named it. We called it Planet Vulcan.
Planet Vulcan.
We were completely happy just making stuff up to explain what we could not understand. And then Einstein says, here's general theory of relativity. Oh, and by the way, it warps space-time close to the sun, and that accounts for Mercury. Vulcan evaporated overnight.
Wow, look at that.
We weren't clutching to it. It was just, we made it up as a secondary accounting for what had a second explanation. We were all in.
You know, can I say something about the importance of Einstein that I like to think about it this way?
Go ahead.
The people in antiquity must have asked the same questions we do, like what is out there? What are we made of? Where are we going? And they had creation myths. Well, we have our own creation myth as of 100 years ago, the hot Big Bang, based on Einstein's relativity. The difference is that we're right. Think about that in human achievement. That is so amazing. So in the last 100 years, the accomplishments are amazing. One more thing I have to add.
Go.
The other thing that changed over the last 100 years, a lot more people get to do science. Instead of back in the old days, it was a bunch of rich white guys.
Yeah.
True.
Now we have a little more diversity.
Right.
Yay!
Gentlemen scientists, yes.
It was the gentleman scientist.
Gentlemen scientists.
So I deviated from the dark matter question, but I just think this is so amazing, the achievements of humanity that we've accomplished.
Social cultural observations are a fundamental part of how any of this works at all and happens. And the pace at which things, I think about it, right. It wasn't just a gentleman scientist. It was, like you said, only men, which meant half the population of the world did not participate in this exercise.
Which is why we're so far behind. If only they had allowed women back then, we would actually know what dark matter is right now.
By now, long ago.
We'd have figured it out. Yeah.
We'd be floating through the... We definitely would have had flying cars by now, for sure. For sure. So does that particle have a name?
Well, there's two of them.
Okay.
There's
two candidates.
Two different candidates, axions and WIMPs, that both have reasons for existence that have nothing to do with dark matter.
Okay. I'm sorry, but WIMPs, like, why would you do that to the particle? Like, really? I mean, seriously, this is a monumental discovery, or
Chuck,
at least
the particle
theory.
has no emotional investment in its name.
It will once it finds out it's a WIMP. Like,
Well, there used to be the MACHOs, massive compact halo objects. Now there's the WIMPs, the weakly interacting massive particles. So
Which is an acronym.
okay,
It's
so
an
yeah,
acronym.
2 different acronyms.
Right.
Yeah.
Yeah, machos and wimps.
MACHOs and WIMPs. Yeah.
Oh,
These were not my invention, these names.
That's okay.
Yeah,
I just want to know, is there particle lunch money anywhere in this equation?
To be taken from them. Right, so you have WIMPs, weakly interacting, massive particles. What makes them massive? When I think of particles, I think of very light objects. So where does massive come in on this?
Well, they weigh about 100 times as much as protons.
Wow.
Okay, so in the particle universe,
Yeah, they're
they have high
huge.
mass.
In the particle universe, they're massive.
Yeah.
They're heavy.
If they're that massive and we can detect protons, why can't we detect these massive particles?
Well, there are 4 forces of nature.
Yes.
Mhm.
And by definition, all mass feels gravity.
Mhm.
But the dark matter doesn't give off light, so it doesn't feel electromagnetic
But let's
forces.
run through the forces again.
Okay.
So we're going to call gravity a force in
Right.
this list. Okay. And then what else you got?
Electromagnetism.
Right.
Which I think we're all familiar with.
Yes.
Light, and it holds our molecules together and our
Right.
particles and the atoms
Everything,
and
everything that's
Electromagnetism.
nice. That's
a
very
demonstration of electro. We can punch Chuck.
cool. Punch Chuck.
Yeah,
That's
a demonstration.
electromagnetism.
Right. If it weren't for electromagnet, I wouldn't have felt that. Cool.
Oh, and I think we did a little bit in Cosmos about this. You're not actually touching each
Right.
other. That there's a field. You're reacting to a field that's set up, and it feels like you're touching them.
Right.
But if you really zoomed in, it's just fields that are
Really?
resisting
Oh,
each other.
okay.
Yeah, I think
Cool.
at this tiniest scale,
Oh.
you're just there's we did like a whole episode on Cosmos on that.
Excellent.
Yeah, yeah. But so
The strong force,
strong
Mhm.
force,
which holds our nuclei together,
yes.
Right.
and the weak force
The weak force, which
is responsible for some types of radioactivity, like uranium decay.
so these are completely different forces. They don't
Yes.
have anything to do with each other.
Nope.
Okay. Yet they all come together to make the world as we know it.
Yeah.
Okay.
Mhm.
So now you have ways that particles know about each other
hmm
and interact with each other
Through these forces.
through these forces.
Yeah.
And I guess what you're telling me is that you've got a massive particle that does not use these forces to interact other than gravity.
Well, no, we think the WIMP, weakly interacting massive particle,
Not no interacting.
it feels the weak force.
Oh.
So of these 4 forces, it's got
That's where you
gravity,
got the weakly.
Oh.
That's where
and
weak
that's
comes
where
from.
the name weakly interacting comes from.
Oh,
Okay.
not that it interacts once every 7 days.
well,
just to be
there are, a reporter
That would
once,
be weekly.
once
That was a joke.
oh,
So-
weekly. Oh, God. Oh, God. I can't believe I didn't get it. Because the answer is actually more like monthly.
Oh, the rate at which you might detect it.
No, there are billions going through your body every second.
Billions of,
If they exist, these
If they-
WIMP particles, there are billions going through your body, but about,
and they go through because they don't interact.
well, except about once a month, one of them would hit one of your nuclei
And
Ooh.
interact.
and
Right.
interact
Okay.
by the weak force.
Oh.
The weak interactions with a nucleus in your body, which is, harmless.
Right.
We think.
Well, let's hope.
That's I think. We hope
We
it's
hope
harmless.
it's
All right,
harmless.
so what about the theory that gives us this particle can tell you that it will interact at all?
So the original motivation beyond dark matter is supersymmetry.
Okay. Supersymmetry. We did
Supersymmetry.
supersymmetry recently on an episode.
Right.
I think we had Brian Green in here.
Yes,
we
we
talked
did.
about supersymmetry.
Yeah.
Where, let me repeat it if I think I understand it. In supersymmetry, we have our particle universe, electrons, protons, neutrons, right? At a higher energy level, counterparts to those particles exist, and we see them in particle accelerators.
Right.
So we have a heavier electron, okay, and heavier quarks, which make up the neutron and the proton. And then there's a third level. Okay, and so there are 3 energy layers in the universe. We only can really access the other 2 in particle accelerators and in energetic places in the universe.
Right.
Okay, so that's the standard model, I guess, right?
That's the standard model.
Okay, so the supersymmetry, are you telling me, I think if I remember, there's an entire other counterpart to all of these particles, not just a 4th layer up there, a whole other counterpart.
For every particle that we have in the standard model, there would be a partner. And it has to be a heavier one so that you double the number of particles, but they're heavier, which is why we don't see them every day. And the heaviest ones decay to lighter ones, until you get to the lightest one. And that is a dark matter candidate. And that
so they can't
makes a great WIMP.
They can't decay into our world of particles.
No, they can't.
Why not?
No.
Wait, if you're making all this up anyway, just declare it so.
Man.
Let it be so.
So let it be written. So let it be done.
Well, there are symmetries, and so they have.
So the symmetries force some of the
They
discussion
have their
on it.
They have their own interactions, their own gauge groups, their own symmetries, and there's a symmetry called R parity, which if that's conserved, then you can't interact with our sector. You
So R
just
stands
decay.
for what in that?
The name is R, capital R dash parity.
Okay.
Doesn't
Doesn't stand for anything.
Okay. So when I see particle physicists hang out together, I hear the word gauge come a gauge symmetries or gauge things. And I can't claim that I know what they're talking about. Is a gauge a thing? Animal, vegetable, mineral, person, place, or thing. How do I come to understand what gauge means?
It refers to, in mathematics, group theory. So there are different groups that describe these different fundamental forces.
Okay.
And so the gauge group for the weak interactions is different than the gauge group for the strong interactions or the electromagnetic interactions.
Okay.
Okay.
All right. So it's a way to
Is it like classifications, kind of, or
organizational?
It's organizational, but it also talks about how things interact with each other.
okay?
Okay.
So within the strong interactions, the way the strong force works, you have the particles that are made, as you know, of neutrons and protons, and inside there you have quarks and gluons.
Right.
And the gauge group defines how those interactions happen.
Okay. So it's a recipe
Gotcha.
in a sense.
Right.
Yeah, I guess you could say that.
Okay. An interaction recipe.
Nice.
Yeah, you're a quark, I'm a quark. Let's check the gauge
exactly.
table
Right.
and see how we interact.
Sounds like a great cooking show. I love it.
And if you're a neutrino, you don't interact with anything at all, other than with weak interactions. So WIMPs are like that, like neutrinos in that sense.
Hey, StarTalk fans. I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk. So this reminds me of the story of the prediction and discovery of the neutrino, where there was some particle interaction and there was a missing accounting of the energy.
So it didn't add up.
It didn't add up.
So
No, all the charges
Everything's
worked out.
there, right.
Everything else was there.
Everything
the
else
charges
is
were
there.
there, but something didn't add up that carried energy away. And so since the charges add up, it had to be neutral.
Right.
And it was a little bit of energy, and so I guess
Pauli.
Pauli predicts it.
Yeah.
Wolfgang Pauli.
Yep.
Oh, okay.
You walk into a room and your name is Wolfgang. People just got to
But
shut up
they
and
just
listen.
give you their wallet.
That's another level of influence.
Exactly.
So Enrico Fermi coins the term neutrino for
Okay.
little neutral one.
Little
Yeah.
neutral.
But there's a prediction that something's there that no one has seen.
Yeah.
And I think that this is a very powerful position to be in as a particle physicist.
Yeah.
By experiment, you trust the laws of physics so thoroughly that when something doesn't add up, you say, there's something else we haven't even found yet. Start looking.
Start looking.
Start looking.
Here's what it might be.
That's a beautiful,
that's
a
the
beautiful
fun
thing.
of being a theorist, that we get to propose things to explain the unexplained data. So we get to be creative. We get to
It's
invent
cool
stuff.
We make stuff up.
We make stuff up. We do sci-fi.
Yeah, but it's not crazy. I mean, you are still constrained.
You're not
Oh, big
making
big
you're not
time.
making it up out of nothing, though.
No.
It's not
No,
a
it's-
story, you know.
Right.
Yeah, you have to satisfy the laws of physics,
Right.
and you have to build on
Yeah.
the existing information you have. So it's
Yeah.
actually not easy to come up with. You come up with an idea on the back of the envelope, and then within a day you realize, oops, this idea is dead. So that's 99% of the time. So for an idea to survive that process, It's not easy, and it has to be a pretty good idea.
The public needs to recognize we joke about you just making stuff up, but you are constrained by nature,
big time,
which is your ultimate judge, jury, and
executioner.
There it is.
Okay.
He gave me the ominous one, of course.
Yeah. No, I love
So
it.
now, wait, back to neutrinos, though. Did we ever prove that that's what it was? That it is the neutrino?
Oh, yes.
It took decades later, but yes.
Right.
Yes.
Oh, yeah.
We discovered the neutrino.
Yeah.
It is very weakly interacting.
Yeah. And they're studied every day. They're created and studied every day in particle accelerators. And in fact, the big push in the particle experimental community in the United States is to build experiments to measure neutrino properties. So you create them in a particle accelerator, you shoot them through the Earth underground for thousands of miles, and then you put your detector on the other end.
Right.
And it doesn't interact with the Earth.
Right.
It's like the Earth isn't even there. Right.
Yeah,
right.
That's right. Yeah.
That's why they say neutrinos are just passing through the Earth all the time?
Right.
Gotcha.
And WIMPs are somewhat like that because they also only have weak interactions, which is why they're so damn hard to detect.
So let's go back for a bit because a theorist needs to make a prediction.
We did. Yeah.
And so you predicted what?
I did the scattering rates of particles off of if you were to build a detector out of some atom. So how much energy would you get from the WIMP hitting that nucleus?
Because most would pass through. So that's the scattering cross section. I think that's what it's called, right?
Yeah.
You send something through. What fraction of everything you send through is actually going to interact?
Right.
And then you get a number, and you design your experiment around that number.
Yeah.
Okay.
Yep.
And are you measuring that interaction by what's left over, what's no longer there, or how are you measuring that interaction?
These interactions are elastic. That means that the particle goes voom, voom, scatters off.
Okay.
But it deposits energy in the detector.
So
you got to measure that energy somehow.
Right. Okay.
Very small amount of energy.
Yeah.
And these experiments have to be deep underground because you have to get away from competing signals that will be a lot bigger. So you have to go a mile underground. And you have to sit there
competing signals
for a long
time. So you have
time.
things like cosmic rays coming in.
From
space.
Other particles that could just actually interfere with
your sun even.
Cosmic rays have electromagnetic interactions, which are that's a much stronger force and happens much more frequently. So you'd have 1 million of those for every WIMP, and you'd never be able to dig out the WIMP. So you got to go underground because the cosmic rays do get stuck in the Earth.
You get stuck in the Earth because Earth and cosmic rays are the same stuff.
Yes.
Right? I mean, there's some transparency, but they know how to interact with each other very nicely.
Shall we demonstrate electromagnetic interactions again?
They interact. But in those experiments, does the interacted nucleus give off light or something, and you see the light? Or is it the temperature of the vat? Or what is it?
Well, there's different experimental techniques.
Okay.
And so either one of those can happen. So you're depositing energy, so that can just be you look for the heat that got deposited. It could create some light flashes you look for. Depends on the type of experiment.
Okay. I have not heard lately, so I'm going to presume we have yet to make such a discovery.
Most of the experiments have found nothing, with one exception, and that's the Dama experiment. That is
Jeffrey Dahmer was a physicist. Did you know this?
No, I thought he was a cannibal.
Oh, jeez.
No,
that's Jeffrey Dahmer. I'm sorry.
No, Donner, what is this experiment? What's
Dama, I don't know what it is. Dark matter experiment of some sort.
Okay.
But it's in Italy, and it's underneath mountains outside of Rome, the Apennine Mountains. So the Dama experiment is seeing something called an annual modulation of the signal. This is something we predicted, that the count rate should be highest in June and the lowest in December. And they've got 15 years worth of data with this annual modulation in it. So they're definitely seeing what we predicted, but nobody knows what to make of it because they won't share their data, which is unusual. Mostly.
Wait, is this because of the sun and a difference in distance from the sun?
It's because the Earth is moving around the sun.
Right.
And that means that the relative speed between us and the particles changes depending on the time of year.
Okay.
The sun is moving around the center of the galaxy, so it looks like we're moving into a wind of WIMPs.
Mm-hmm.
And so it's like when it rains on your windshield. It looks like you're going into...
Like you drive into a storm.
It looks like it's coming at you.
So it looks like it's coming at you. Yeah. And that relative speed is really important, but because the Earth goes around the sun, when you're going into that wind, you're going to get a higher count rate. And when you're coming
and
out of it...
And it's coming where? The center of the galaxy? Where's it coming from?
Well, we're going around. The sun is going around the center of the galaxy.
Right. But
So there
why
is
would
no-
it be two different directions?
Oh, okay. So the two different directions are just because the Earth is going around the sun.
Mm-hmm.
Okay, so the sun's going like this, and the Earth is going around it.
But which way the
The
wind's
wind
coming
is
in?
coming this way
Why is it coming from? That's what I'm asking. Why
because
is it,
the sun's going that way.
oh, okay.
It's just the motion of the sun
Just the sun.
that
So
creates
therefore,
an
this is
artificial
like the ether.
wind.
We're either going with it or against it.
Yeah.
Got it.
Yeah. Yeah.
Got it. Okay.
So it's not a real wind. It just looks like a wind because we're moving into it.
Okay. Now, if dark matter doesn't interact with us, it kind of also doesn't interact with itself, or does it?
Oh, yes, it does. It annihilates. So when two dark matter particles hit each other, they annihilate, which means they turn into something else.
Then how can
Wow.
you make an object out of dark matter?
I don't make an object
I
out of
thought you
dark
made
matter.
a
Do
dark
you
ma-
make objects out
I
of
thought
dark
you
matter?
made a dark matter star.
No, dark stars are made almost entirely of hydrogen and helium,
Okay.
99.99%, and it's a little bit
Which
of
is
dark
regular,
matter.
like all
Right,
stars,
right,
like
yeah.
all stars of that. Okay.
Yeah,
Mhm.
and no, it's only hydrogen and helium from the Big Bang because these are the first stars that ever formed.
Got it.
So they don't have anything else in there. No carbon, nitrogen,
No,
oxygen.
all I meant was all stars have hydrogen and helium in them. That's all I meant.
Yeah.
okay,
So
okay.
it's ordinary matter, but it's powered by dark matter. So that's because you have a lot of dark matter in there, and those dark.
Left over from the early universe.
Okay, let's back up. The dark stars would have been the first stars to form in the history of the universe when it was 200 million years old, and we're now at 14 billion years.
And dark,
Okay.
this is your baby. These dark
That's
stars.
my baby.
You
This
birthed
is my,
these.
This is my baby.
Yes. Okay. Go on.
Yeah.
Go on.
Yeah. And back in the early universe, these things would have formed at the centers of protogalaxies,
Yes.
small objects that are going to merge together to make our
It's
galaxy
where the
later
action
on.
was. The gravitational action was.
Yeah. And so smack in the middle of these protogalactic objects, they're called mini halos. That's where you would have collapsing clouds of hydrogen that are on their way to forming stars.
Mm-hmm.
In the standard picture, they keep collapsing and make tiny little objects a thousandth of the mass of the sun, and then accrete back up to about 100 times the mass of the sun. But nobody asked, well, yeah, but if you're smack in the middle of the protogalaxy, what about the dark matter? What does that do?
Right.
So that was a question that we asked. And
You
it
would be
changes.
enclosing some volume of dark matter in doing so.
Well, there's a lot of dark matter at the center of our galaxy, at the center of the protogalaxy.
Okay.
The fact that you're smack in the middle is what counts,
Got it.
because that's where you got a lot of dark matter.
Got it.
And when you got a lot of dark matter, you get a lot of dark matter annihilation.
Mm-hmm.
And why the coalescing of dark matter at the
Because
center?
it
like
responds
that?
to gravity. We knew that.
Oh, that's right. Because
Yes.
at the center of every galaxy, there's a black hole. Is that the deal?
no,
Oh, it doesn't matter about the
Doesn't
black
matter
hole.
about the black
no,
hole.
No,
Okay.
it's just, yeah, if you go to the center of any massive object, a galaxy, a cluster, anything, that there's a ton of dark matter in there.
okay.
And then as you move out, it gets less and less dense in terms of the dark matter.
Interesting.
So
Yeah, just to be clear,
Go ahead.
there's more. If dark matter is a thing,
Right.
there's more of it than our matter.
Right.
So it's been analogized. I love this analogy. Correct me if I'm wrong here. That when we look at our galaxies and the light from them, the stars, this is sea froth
Mm-hmm.
on an ocean of dark matter that's what's actually driving where everything collects in the universe.
Exactly.
Is that a fair characterization?
Yeah.
that's great. Yeah. It's
Yeah,
good.
and here we are thinking the visible stars and galaxies, that's the thing. No, the dark matter is dictating everything.
You know, this is a weird thought. The way stars are moving around the center of the galaxy, they would get flung out of the galaxy if it weren't for the dark matter providing the gravitational pull to keep them in.
Right.
So we desperately need dark matter, even for the Milky Way.
Vera Rubin first showed that.
Yes.
1976.
Yes.
That you figure out how fast all the stars are moving. So
Right.
you're going too fast.
Right. To stay.
To stay.
You're going too fast to be.
You have enough speed to escape, and you're not
Right.
escaping.
Exactly.
Something's
How
holding-
is that kid staying on the merry-go-round? He's not fat enough to stay on the merry-go-round.
Massive enough.
Massive enough. Very good. Very good. Yeah, he should have been flung off.
Flung off. And so some extra forces are holding it.
Right.
And behold this mysterious
Dark
problem.
matter.
See, this is what is so fascinating about the whole thing. It's like you guys it's all the information allows you to infer all this other information.
Yeah.
Crazy.
That's how it works.
It's freaking crazy.
That's how it works.
Yeah.
And it worked because the information that we trust
Right.
we trust on a level that gives us the confidence that the next thing we invent might have some validity. Because this worked.
And
if this worked,
and we have to test it. We have to find it. We have to prove it experimentally or observationally.
Right.
Yeah.
Wow.
Have you ever wanted one of your questions on the universe answered? We all have questions about that. And JWST, which is exquisitely tuned to observe the early universe and the birth of galaxies, seems to me ought to be right where you need it to be to test your hypothesis.
Well, these dark stars start out when they first form being about as massive as the sun, but they're really weird. They're in distance 10 times, their radius is 10 times the distance between the Earth and the sun. Isn't that weird? They're big puffy objects, and they're very, very cool. They're not hot, no fusion, no core, nothing. They keep accreting and growing until they can get 1,000,000 times as massive as the sun and 1,000,000,000 times as bright in the early universe. Now you got something you can see, you can look for.
Whoa, because you're...
Wait. So if it's not undergoing fusion, where does the brightness come from?
Dark matter heating. Dark matter heating.
What? There it is.
Yep.
Dark matter. Don't you run out of dark matter? It just keeps annihilating itself. You're going to run out.
Well, there's an awful, you're right. Eventually you will, but then that mini halo is going to merge with other mini halos. And if the dark star stays at the center, it can keep going. It can keep getting more and more dark matter.
Wait a minute. Wait. So if your dark star uses up all the dark matter in it, then it's just a big ball of gas.
Yeah. And guess what happens to the million solar mass, something that weighs 1,000,000 times as much as the sun with no heat source anymore? Klump, black hole.
Whoa.
Supermassive black hole, which no one knows how to
explain. So you can explain
the big black hole problem. We
don't know
explain
how to
it.
make a big black hole.
No, we don't.
We had no idea.
There is no cosmic shovel to make a big black hole.
And so, and you make it for free.
Yeah.
Wow, look at that.
You know how I said you try ideas and they're usually dead within 3 days? Well, this was the opposite. Somebody told to us, "Oh, did you know you just solved a big problem?" I said, "What problem?" The big black hole problem.
The massive black hole in the center of galaxies.
Supermassive black holes.
We were saying, well, there must be some way to channel matter. For the big problem here, unstated, is it's very hard to get to the center of anything.
Right.
If you have any motion at all. Because if you can go to the center, it meant you had no angular momentum around it. You have to so people say, let's just take our garbage and just send it to the sun.
Right.
Can't do that. Because all of our garbage is moving at 30 kilometers per second with the Earth around the sun. You have to stop. You have to take that speed to 0. Then it'll fall towards the sun. Right. If it has any other speed, it's just going to orbit the sun.
So it's go with you. It's going on the ride with you.
It could, and it would be annually modulating by going to Earth, going around the sun, the garbage going around the sun.
Yes, right. that is so cool. No, I've never heard that before. But you're absolutely right. You can't just shoot your garbage at the sun.
At the sun, because it's going sideways.
It'll just start falling around the sun the same way you do.
Correct.
That's amazing.
And you know what it'll do? It'll have an orbit that'll have it re-intersect Earth.
Right.
Yes.
And then your garbage just comes back.
Right back in your face. Okay, so you solved the supermassive black hole problem.
Wow.
So they'd be accreting the dark matter themselves, wouldn't they?
What, the black holes? So most of the accretion is ordinary matter. The dark star accretes more and more ordinary matter.
No.
More and more hydrogen.
If the supermassive black hole is in the center of the galaxy, and dark matter centers on the centers of galaxies, rather, galaxies center on the centers of the dark matter, why wouldn't the black hole also be eating dark matter?
Yeah, I guess it is.
Okay.
And then there could be more dark matter around there that's annihilating, and you can look for signatures of that dark matter annihilation.
Okay, so when it annihilates,
the same annihilation that happened in the early universe.
And does it give off photons that we...
Yes.
Regular photons,
yes.
Not dark matter.
Nope, regular photons. Yep. They produce gamma rays, so high energy photons.
Whoa.
That people in the Fermi satellite is looking at the gamma ray sky.
Named after Enrico Fermi.
Named after Enrico Fermi, and it has...
It specializes in what part of the spectrum?
Gamma rays.
Gamma rays, okay. Mm-hmm.
And it sees an excess coming from the center of our galaxy. And there are those who speculate, oh, that's dark matter annihilation, which would be so cool. Now, the trouble is there's a lot of astrophysics at the center of the galaxy.
Yeah.
There are
a lot of things that can make that.
There are a lot of other things that could make the same signal, so we're not sure.
Okay, but Katie, when you get your Nobel Prize, will you invite us to Stockholm?
Well, you know, already spent 10 years in Stockholm. I've already gone to that Nobel party a number of times.
Oh, so
And
it's
I have,
old- it's
and
old.
hold on,
news.
no, my point is I know exactly how to sneak people in.
Sweet.
Oh, which back door lets that happen? No, I wouldn't want you to sneak in. I want you to announce us.
I will invite
To-
you.
to
No, I
the-
don't want to be snuck in.
I want to be announced. Neil Tyson and Lord
Chuck
Nice.
Nice.
Lord Nice. Right. All right. So you solved the black hole problem, the supermassive black hole problem.
That's amazing.
How does JWST contribute to this?
We had this idea in 2007, the idea of dark stars. And then in 2010, John Mather, the Nobel laureate, who is the guy behind the James Webb Space Telescope, said to us, hey, give us predictions. These are bright early objects. We can look for them. So we did. So we predicted what the spectrum should be. So how much light at different frequencies would be coming out of these objects. And they're only made of hydrogen and helium, so you better not see signs of any other element in there.
Mm-hmm.
So when the James Webb turned on, we were ready to compare the early universe objects that they're seeing to our dark star predictions. Now, one dark star can be as bright as an entire early galaxy of stars. And so telling the difference, well, there aren't very many spectra yet. But at the time, we did this a year ago, there were 5 objects with spectra that we could get our hands on, and 3 of them were dead on, perfect matches to dark stars. But we don't know
These
yet.
5 objects were those mysterious objects in the dark ages
Yeah,
of the universe.
absolutely.
I think we did a thing on that. There's a point where before galaxies formed,
Right.
but matter had coalesced. So there's this gap, before stars had formed that we all just call the dark ages.
Mhm.
And then James Webb turned on, found 5 galaxies doing the backstroke in the dark ages.
Right.
Who ordered that? Nobody ordered that. Katie ordered that, apparently.
Nice.
Well, the other thing that's nice about this is the standard model lambda CDM of cold dark matter and the dark energy that everybody considers a standard.
So CDM, cold dark matter.
CDM cold dark
Right,
matter,
And lambda is Einstein's
cosmological constant.
which gives us the acceleration of the universe.
Yes.
Yes. Okay.
So according to according to that model, some of these objects they're seeing from the early universe are too massive. They'd have too many stars in them. It doesn't
didn't
make
have time to become that massive.
Well,
That had to
all
be
of
it,
the
right?
all of the ordinary matter of the universe would have had to go into these things, and that just doesn't make sense. You don't have enough ordinary matter to produce that many stars.
Hmm.
So, all right, we'll take some. They're dark stars.
Oh,
Wow.
okay.
Yeah. We don't know yet because you need better spectra. You need more details.
But the rudimentary
But it
spectrum right
makes
now.
sense.
The rudimentary
fits.
spectrum matches.
And just to remind people, so you said it, I'm going to say it again, that when you take a spectrum, you want to know how much energy is coming in at different wavelengths.
Right.
And the shape of that spectrum is something, in principle, you can predict with your models.
Yep. Yeah. Mhm.
And so if the spectrum matches up, so it's not just how much energy is here in this one spot, or how much energy is there, is what is the full. Once you have all these matched up, that's a pretty good prediction right there. It gives you some confidence.
It's wild.
So what we need in the future is to wait for more data because some of those objects that are coming in are going to be lensed. In other words, there's a bunch of mass in front of them. It will magnify the images, and then you're going to see in more detail, and you'll be able to tell, oh, is that a dark star with exactly the hydrogen and helium that we predict, or is it something else that has carbon, nitrogen, and so on? So we're waiting for more data.
I have some memory that some people are calling, they have an idea called the dark Big Bang. Is that a thing?
Yeah. We invented that. I get to say it. We invented that.
Okay.
Wow.
Yeah,
Okay.
yeah.
Okay.
Well, we were realizing that people talk about there was an inflationary epoch of accelerated expansion in the very early universe. And at the end of that energy, the vacuum energy gets converted to ordinary stuff. And that's where ordinary matter would come from. And people usually think, oh, you make matter, ordinary stuff, standard model particles, you make dark matter, you make it all at once. And we had the idea, well, wait a minute, what if you don't? What if the dark matter is produced later? And so we're going to say, okay, there's inflation early on, but then there's a dark sector. Now we're talking about dark matter that does not at all interact with ordinary matter, which is, it's different. So if in this dark sector, you could have a smaller vacuum energy that later on converts to dark matter. You'd create the dark matter later, and the time that
what does that buy you when you do that?
What we wanted to do was push it forward all the way to the time when matter radiation equality, in which case that would be kind of cool that you're producing dark matter right then. But we were unable to do that. So the farthest forward we could push it is 1 month after the regular Big Bang. So we have the dark Big Bang at 1 month, but that's human scale, which in the early universe is a really, really long time.
Given the sequence of events that unfolded, a bazillion things happened before a month passed.
Oh, God, yes.
Yes.
Okay.
Yeah.
And we also talked about what kind of dark matter particles you would get out. And so we have things like cannibal dark matter. We have darkzillas. We had a lot of fun.
Darkzilla.
Dark. We have the dark WIMPs. All kinds of possibilities that are non-standard.
I never heard of these particles, but I don't want to mess with Darkzilla.
Well, Darkzilla's pretty heavy, yeah.
How about Dark Rodan?
The sculptor? Rodan?
No, Rodan. If you mention Godzilla, you got to mention Rodan. Rodan was the
arch nemesis of Godzilla.
Yeah. So
he was?
Yeah.
Oh, I thought you were talking about the sculptor.
Yeah. So Rodan was basically a pterodactyl,
like a pterodactyl.
I think, but it was supersonic.
Oh.
So it would fly, and like buses would tumble behind it. If Darkzilla has this huge mass, and Dark Cannibal, what did you call it?
Yeah, we have dark cannibals too.
Dark Cannibals. What do those do?
Dark cannibals eat themselves. So you start out with 4 of them, and when they interact, then you end up with only 2 of them.
Ooh,
oh, man!
And 2 of them got bellies at the end, and they. Okay, so they don't just annihilate or anything; they actually consume them.
Yes, they consume.
And these are
themselves.
properties you have derived from all of your equations and your analysis.
Well, these are different possible dark matter particles that could come out of the dark Big Bang from these bubble collisions that people hadn't really thought about before.
All right.
So these are new ideas. Yes.
Okay, so there are people with other hypotheses that are out there, as there, of course, there would be.
Yeah.
Is there anyone who's specifically critiquing your work? Do you have a nemesis?
No, I'm happy to say.
Good. That's good.
No.
So it is afloat with the other ideas, and ultimately the data will show.
Yes.
Excellent.
So do you actually, I'll ask you both, do you actually care if somebody, if their theory ends up proving out and yours does not? Does that hurt at all?
Of course.
Okay.
But I honestly think that dark stars, as precursors to black holes, are better than the other candidates, because I think some of
Says
these
the person who came up with it. I'm just saying.
True. So, but if one of those proves to be right, of course I'll be disappointed.
But I get to say, as a non-participant in this exercise, in this research exercise, that if we have any solution at all, I'm celebrating.
Yeah. Okay. Right. Yeah. Right.
Because it advances our understanding of the known universe.
You know, there are people, actually it's the opposite. People have picked up on our ideas, and there's a group in Sweden, and they're jointly with University of Virginia, who have massive grant money to study dark stars as precursors for the supermassive black holes. And they're the ones who can give you the arguments why the other competing models have problems. And so it's kind of the other way around. People are picking up on it.
Right.
That's a good sign.
That's a great sign.
Yeah, it's a good sign.
Yeah, that is a good sign. Yeah.
And this is not something that you sought specifically to. Yeah,
not
this
at
was
all.
just actually
That's what makes it
presented
better.
to you as you were seeking other information.
Now when we first came up with these ideas, we encountered massive resistance. So I remember going to when the idea of dark
Massive
stars.
propagated by what particle? by what
The macho.
blows on.
That was macho.
Guys, okay, humans.
Guys, human.
The guy particle.
The guy particle.
It's the guy particle.
The guy particle.
The guy.
Total hater.
Yeah, and particle physics is like the last bastion of guydom.
Right.
Right. Okay.
Yeah. So we went to a conference, and at Berkeley, one of the leaders in the field said, this could radically revolutionize everything. Go to this conference and just put up a poster. Well, I didn't know how to make a poster, so we just put up a couple pieces of paper. And
Just a poster at a conference. There are people who give talks but there's not enough room for everyone in time to everyone give a talk. So they have poster sessions where there's drawbacks and benefits. Posters, you're not as visible,
Right.
but you can have a one-on-one conversation with someone
Right.
that can be very enriching and deep.
That's called a science fair.
Science fair.
Science fair. Well, this is the only time in my life I've ever done a poster. So
Okay.
I usually do talks.
Okay.
But this was so new, there wasn't time to make a talk, right? But people were extremely skeptical, shall we say. I heard a grad student calling us crackpots. I'm not kidding.
Oh.
Yeah. And then that same grad student later ended up writing papers about it. So we had converts. That was really weird. And we had guys saying, why are you inventing WIMPs? I'm like, what? Why don't you use the Higgs for the dark matter? The Higgs lasts 10 to the minus how many seconds? You
Right.
can't build dark
Yeah,
matter out of it. So we had a lot of contrariness, shall we say. So when you
But
have
you'd
a new
expect
idea,
that. Wait, you expect that for a new
happens
idea.
every damn time.
It's
okay?
out of respect
every time.
that they're attacking you.
It was pretty, I was pretty shocked by these comments. But the same people, those two people, both ended up writing papers on dark stars independently.
That's satisfying.
Well, I mean, if you have,
Did they come back and apologize?
No, but if you
Okay,
have
give me their name.
Yeah.
Chuck, we got a guy.
We know who.
We got a guy
Yeah,
who
we got
can-
somebody.
you got a guy.
We got somebody can talk.
Tell you later.
We'll talk.
Yeah, we'll
Tell
talk.
you later.
Let us know.
So that's gratifying. If the science is right, people are going to go, oh, okay, they'll catch on eventually.
Yeah,
So that
if the science
happened.
is right,
And that
then
was
they're
back
just-
in 2007. Okay?
then they're just
So-
assholes, right? I mean, if the science is right, and
Yeah,
they're revealing that they can't even think outside their own box.
Right.
Right. So you go outside the box, you got to expect this kind of stuff. And I've encountered it a lot. But in the end, if the science is right,
If
then
it's right, it's right.
it's right.
Exactly.
So,
And if the science is right, it has nothing to do with how good a talk you gave
yeah.
or how who even paid it. It doesn't matter.
If you give good talks, then people hear about what you're doing. That's important.
No, but but if the science is wrong,
Yeah.
they'll hear about it and they'll just delay when it has to be put in the trash bin,
True.
right?
Right.
Yeah.
That's correct.
Okay.
Yeah.
So this goes back to the idea of, am I working, I can be creative, but is it sci-fi? No, because it has to, in the end, hold up both theoretically in terms of the mathematics, and it has to not be ruled out immediately by some other bound that you didn't imagine. And so it has to hold up over the long term.
Yeah. Well, Katie,
Wow, that
thanks
was
for
something.
catching us up on this.
Yeah.
I did not know all the latest
Who knew?
Dark.
I mean,
dark to get dark dark universe. I know. I'm delighted to learn that this remains an active, tested, hypothesized field.
Yeah.
And so should we forgive her for being a particle physicist and suggesting a particle as the result?
Yeah, at this point, I'm like the student who wrote the paper.
You're convert.
I'm a convert.
Total
I'm
convert.
like, this is great.
Total convert. All in. So Katie, thanks for coming.
Thank you,
And-
Neil.
and-
Thank you, Chuck. Great to meet you.
It's great to meet
And
you.
you're
too.
based in Austin, but you came through town because, as you said offline, you presented at the World Science Festival.
I did last Saturday.
Yes,
It was
and you know who
really
runs the
fun.
World Science Festival?
Brian, right?
Brian Green.
Yeah.
Yes, he's a friend of our show.
Yeah.
Yeah, and he brings together scientists and artists and the cultural forces just to show that science is a part of our everyday life. Does it every year. Might have had a COVID hiatus, but every year. And that brought you through town. And your son is getting married.
My son is getting married. on
Congratulations.
Saturday.
Mazel
Yeah.
tov.
Okay.
That's great.
Yeah.
You got it.
Yeah.
All right, Katie, thanks again for coming through.
Thank you.
All right, this has been StarTalk, the Dark Universe edition with my friend and colleague, Katie Freese. Chuck, always good to have you.
Always a pleasure.
Unlike so many other exploits in our civilization, science is exquisitely tuned with its methods and tools to establish that which is objectively true and discard that which is objectively false. And we accomplish this by putting forth an idea and testing it, challenging it, attacking it even. Because there's so many ideas, there's so many ways the universe could be, but there's only really one way that it is. So that ultimately, no matter what ideas you have, no matter how you think the universe can be, should be, ought to be, it is the ultimate judge, jury, and executioner of any thoughts you have. And to chat with Katie, my friend and colleague from the particle physics universe, about how they take known ideas about the universe that have been tested and then extend them into realms that are not yet tested, I'm just reminded about not only how science works, but how beautiful it is when it makes discoveries derived from it. That is a cosmic perspective.